good morning, everyone. I hope you're all doing well. So this is what we were working on last time. Rigid body kinematics. So the angular momentum about the rigid body about its center of mass is hc. That's equal to ic omega. What is ic again? The inertia tensor about the center of mass. The angular momentum of a rigid body about a material point P on the rigid body doesn't have to be the center of mass, it's HP. HP and HC are related, and we showed this relationship. We actually showed all of the relationships that are on the board here. Now from the last one, we can obtain a set of scalar relationships that are called the parallel axis theorem, which we probably practiced a little bit in the exercise in the discussion section yesterday, right? Okay, so what I want to do first is I want to write this expression here in matrix form. So I'm going to take the rigid body, consider some corrotational basis on the rigid body. Then I can write this matrix IP as IP ij sum, this would be double sum, equals the sum over I, j equals 1 to 3 equals 1 to 3 of IP ij ei 1 ej. And remember, that's a sum of 3 terms. I goes from 1 to 3, j goes from 1 to 3. That's a sum of 3 terms. I can also express IC on the same basis. Now, what about RC minus RP? I will call this vector So now I can write IP 1, 1, IP 1, 2, IP 1, 3. With me so far? Any questions? Questions? Same thing for IC. So that's the identity times the scalar magnitude of RC minus RP. So that's AX squared. I'll give you a minute to think, what does the last matrix look like? What does the last matrix look like? So you're going to take this term, ax plus ay plus ac plus az, and bond product with itself. So what is the coefficient of the ex bond ex term going to be? Ax squared, right? What about the coefficient of the ex bond ey term? Ax ay. Does that make sense? Any questions? So then I can read off, how many equations I can read off from this big scalar equation? How many scalar equations can I read off? Sorry, how many scalar equations can I read off from this big matrix equation? Can anyone guess? Show me with your fingers how many scalar equations I can read off of this. So this term is equal to this plus this plus this, right? So you can say 6 or 9, and then 3 of them are the same, so 6 independent equations, okay? So for example, for the first one, A11 or AXX, IPXX is equal to ICXX plus AY squared. I'm thinking I'm forgetting something, which I think is a mass that multiplies these two. So I'm forgetting an M term here. M. Okay, so that's for a moment of inertia. For example, for a product of inertia, IP xy okay. And these set of 6 equations that we can read off from this matrix equation are called the parallel axis theorem. That's called the parallel axis theorem. So it relates the moment of inertia about of a rigid body about 2 points two points P and C, with the axis or basis at P being parallel to the basis at C. Rigid body, I have 2 points, the center of mass and point P. For these relationships to hold, the basis needs to be the same. So the first condition is that the basis needs to be the same at the 2 points. The second one is that it only applies between the center of mass and some other point. It doesn't apply between any 2 material points on the rigid body, okay? So the parallel axis theorem does not apply between any 2 material points on the rigid body. It needs to apply between the center of mass and then some other material point on the rigid body. So I think what you did in the discussion section yesterday is that you looked at the cylinder or one of the shapes in the table of moments of inertia. For example, the rectangular parallelepiped, and you were able to relate the moments of inertia about of the shape about an axis or two axes that are parallel but passing through different points. Okay, and you were able to use this formula, and you were able to get the same equation as the book, as the table. Any questions? Questions? So we will be using the parallel axis theorem a lot. We'll get some practice later in the lecture today. Okay. Any questions? Now I want to start looking at the kinetics of a rigid body, meaning the balance laws. Before that, I need to introduce one concept, the radius of gyration. Okay, so let us consider a circular hoop. Okay, so let's consider a circle of mass m, radius r, and the EZ axis is perpendicular to the plane of the circle. I want to calculate the moment of inertia of the circle about its center of mass about the z axis. I C Z Z. What is that equal to? I'll remind you of the formula, but ICZZ was the integral of over the body of x squared plus y squared dm. Yeah, of x squared plus y squared dm, where x squared, where basically r minus rc was equal to x ex plus y ey plus z ez. Okay, for where C is the center of mass, and then R is the position vector toward any material point of the rigid body, and we're summing over all possible material points. So then what is the ICZZ for the hoop? And the hoop is a very, very special case. It's a very simple calculation actually. What is x squared plus y squared for the hoop, where x and y are measured from the center of mass? It's r squared, right? It's a constant. It's r squared. Oops. So that's the integral over the body of r squared. I can take it outside because r is constant. It's the same for all the points on the hoop dm. And what's the integral over the body dm? That's the total mass of the body, mr squared. So really that's the simplest moment of inertia calculation, the moment of inertia of a circle about its center of mass, about an axis perpendicular to the plane of the circle passing by its center of mass. Really the simplest moment of inertia calculation. Any questions about this? Okay, so we didn't explain what the radius of gyration is yet. So sometimes what we do is that we have a complicated rigid body. We have a rigid body that's very complicated. Now, instead of reporting the moment of inertia of the rigid body or reporting the geometry of the rigid body, instead of reporting the moment of inertia of the rigid body, say about EZ, or the geometry of the rigid body, what we say is that the rigid body has some radius of gyration. Say the rigid body has a radius of gyration kz about EZ passing by center of mass. What does this mean? This means that the moment of inertia ICZZ is equal to the mass of the body times kz squared. Times the radius of gyration squared. So sometimes instead of reporting the moment of inertia, we report the radius of gyration, and they're related by this formula. Now, seeing the definition of the, or saying the moment of inertia of a circular circle hoop of mass m radius r, and then this definition of the radius of gyration, what is the relationship between the two? Yes, exactly. It's kind of saying that this randomly shaped object has a moment of inertia about EZ passing by C that is equivalent to some hoop with the mass, same mass as the rigid body, but with radius equal to the radius of gyration. It's kind of drawing an equivalence between the two. So yeah, instead of reporting the moment of inertia, sometimes they report the radius of gyration. Why do we call it a radius of gyration? Because it it goes back to the circular hoop. Okay. And you could be given a radius of gyration about any direction, x, y, z. Okay. Now what I want to start to look at is the kinetics of a rigid body. How many degrees of freedom does a rigid body have? 6, right? 3 rotational, 3 translational degrees of freedom. So then how many balance laws do we need to describe the motion of a rigid body? Yeah, we'll need 6 scalar balance laws to be able to describe the motion of the 6 degrees of freedom of the rigid body. So these 6 scalar balance laws are going to come from 2 vector balance laws in 3D, the balance of linear momentum and the balance of angular momentum. So the balance of linear momentum for a rigid body, balance of linear momentum, or Euler's first law, that just says that F equals G dot, where G is equal to mvc. So the sum of forces acting on the rigid body are equal to the total mass of the rigid body times the velocity times the acceleration of not any point on the rigid body, the center of mass. So F equals mac, the acceleration of the center of mass. So that's the balance of linear momentum. That's Euler's first law. The balance of angular momentum, that's Euler's second law. And this has 3 forms. The first form is that about the center of mass C, mc is equal to h dot c. The second one is about a fixed point O. So this second form cannot always be applied because we don't always have a fixed material point on a rigid body. You can imagine me throwing my phone in the air. There's no fixed material point on my phone. So C does not always apply. The third one is about any material point on the rigid body. the general plan is this. A rigid body has 6 degrees of freedom when it's unconstrained. 6 degrees of freedom, I need 6 scalar equations to describe the motion of the rigid body. 6 scalar, they're going to be differential equations. These are the balance laws. 3 come from the balance of linear momentum, and 3 come from the balance of angular momentum. We will show that these balance of angular momentum equations are all equivalent. Okay? And whenever I add a constraint, I add an equation, which is the constraint equation, but I also add a constraint force, which is an unknown. So whenever I add a constraint, I add another equation, another unknown. Okay? So now I want to do three things. I want to figure out how to calculate F, MC, MO, and P. I want to show that these equations are equivalent, and then I want to be able to calculate the other side of the equations, the angular momentum side. So our plan, number 1, is to calculate or define what F is, what MP is. Number 2, show that A, B, and C are equivalent. And 3, show how to calculate the derivative of the angular momentum. So let's start with 1. So I'm considering a rigid body. I could have point forces acting on it. Up to Fk. I could have a distribution of forces acting on it. So a segment where I have a distribution of forces acting on the rigid body. I could have couple moments acting on the rigid body. ME. What is a couple? Yes.
Two forces that cancel each other out and create a moment
Yes. Yes. It's a pure moment that acts on the rigid body, which could be the result of 2 forces that cancel each other. So if I have some bar and I have 2 forces acting on it, equal and opposite, the net result of these 2 forces is that if I sum them, I get that the net force is 0, but the net moment is not 0. So the net result of this is a couple. Another source of a couple could be, for example, a torsional spring, a spring that looks like this. You've probably seen this before. You can find them in hair clips. Also sometimes in door hinges. I added a video about different types of springs in the notes. You can check. Okay, so what is the sum of forces acting on a rigid body? That's easy. That's the sum of all the forces acting on the rigid body. F is the sum of all forces acting on a rigid body. So if I get rid of these force distributions for a second, F is just the sum of Fi, I equals 1 to K, to N. No, F equals 1 to K. It's the sum of the discrete forces acting on the rigid body. Now, what about the sum of moments about a point P? How do I calculate the sum of moments acting on a rigid body? Exactly, that's the moments of all the forces about P plus what? Yes, any couples. So between this system, I can find an equivalent system that looks like this. Some point P with a couple MP acting on it, and the resultant force F. This point P in particular could be the center of mass. So the sum of moments MC about the center of mass, I can take P to be specifically the center of mass C, and I'll get I equals 1 to C of Ri minus Rc plus Fi plus Me. And there's a relationship between these two. I can say that MP is equal to the sum Ri minus Rc plus Rc minus Rp plus Fi plus Me. Any questions so far? Questions? So I'm going to split this into two, and the first term is going to be MC plus Rc minus Rp plus F plus Me. Okay, the reason I'm doing this because I'm going to use these equations to show that this balance of angular momenta are equivalent, which is leading me to step 2. So I'm erasing the board here. Okay, so I want to show that these A, B, and C forms of the balance of angular momentum are equivalent. I'm going to start with one of them, maybe C, and show that I get how I get the other two. Yes?
For the last equation, would ME be factored into the MC?
Oh, yes, that's correct. Yes, you're right. Thank you. Anything else? Okay, so MP is equal to H dot P plus Vp minus Vc cross G which is equal to H dot C plus Rc minus Rp cross MAC. How can I show that these two are equivalent? How can I show this equality? Any ideas? Take a minute, think about it, chat with your neighbors. How can I show this equality? Equality I, that H dot P cross plus Vp minus Vc cross G is H dot C cross or plus Rc minus Rp cross MAC. I think all the equations we need are on the board. So any ideas where to start? maybe I can start with this side, h dot p plus Vp minus Vc cross G is equal to, well, what is Hp is up there, right? So h dot p is h dot c plus the derivative of the second term is Vc minus Vp cross G plus Rc minus Rp cross G dot. Okay, and then plus cross G, these two terms cancel out, and I'm left with whatever I wanted to show. So again, what did I do? I wanted to show that this term is equal to this term, so I started with this term, and I replaced h dot p by Hp is equal to Hc plus Rc minus Rp, the second equation up there. I took its derivative, replaced, and I got what I needed. Now, the second thing, any questions? Questions. The second thing I want to show is that I want to show that MP is equal to h dot p plus Vp minus Vc plus G. I can simplify this to get MC is equal to h dot c. So, any ideas on how should I start? I think all the equations I need are on the board. So, any ideas on how to start? Exactly. I could replace MP by MC plus Rc minus Rp cross F and maybe I use this form. Instead of showing this, I'll show the other one. This one. Okay, cool. These are quite simple. MAC and F are the same, and I'm left with MC is equal to H dot C. So these were quick. So I've basically showed that the two expressions in C for the angular momentum side are equal, and A and C are equal. How do I show that B and C are equal? It's also pretty simple because P is the general case of any material point on the rigid body, and O is a special case of that material point having zero velocity, right? So if I look at equation C, and if I take P to be O, where VO is 0, do I recover B? So setting P equals O with VO equals 0 in C, in C this should give form B. So then all the forms of the balance of angular momentum are indeed equivalent, A, B, and C. Make sense? Any questions? Okay. So before I do step 3, which is calculating the derivative of the angular momentum part, we're going to do a few problems from set 19, rigid body translation. Okay? So the rigid body translation part is going to help us kind of practice the force moment side of the equation, because when a body is translating, what is the angular velocity of the body? 0, exactly. So what is the angular momentum of the body about its center of mass? 0. Why? because omega is 0, so HC, which is IC times omega, is going to be IC times 0, which is 0. So then the derivative, the angular momentum about C, the derivative are going to be 0. So we're going to first practice these, and then we're going to look at the derivative of the angular momentum. So let us consider, oh, I gave you all my sheets. I think, thank you. Let us look at problem 1. Any extra sheets anywhere? No, okay, great. Thank you. Okay. So let us look at set 19, problem 1. A uniform slender rod rests on a car seat as shown. Determine the deceleration A for which the rod will begin to tip forward. Assume that friction at B is sufficient to prevent slipping. So what is happening? What is happening to the car? Is it accelerating or decelerating? Decelerating. So has it ever happened to you where you're pressing on the brakes too hard that things topple over in the car? Yeah? Happens to me all the time. I'm kidding. I'm a great driver. It doesn't happen to me ever. I'm kidding. So what we want here is that, okay, a uniform slender rod rests on a car seat as shown. Determine the deceleration A. So the car is decelerating, for which the rod will begin to tip forward. The rod is not tipping forward, but it will begin to tip forward. What does that mean, like, in terms of forces? If the rod is about to tip forward, but it hasn't tipped forward yet. So what is the angular velocity of the rod? 0, because it did not tip forward yet, but it's about to tip forward. So what does that mean in terms of forces? What is it?
Net force is equal to 0.
Not quite. So if I want to draw the free body diagram of this rod, how many forces are acting on it? Okay, so I have rod AB, gravity is pointing down. What are the forces acting on this rod? The weight at which point? Center of mass. At the center of mass. I'm going to call the center of mass of this rod C. So, great point. Now we're talking about rigid bodies. The point of application of the force matters, right? It matters if the weight applies at A, B, or C. I can show you that the weight is always going to apply at the center of mass, and it's not going to have a resultant moment. So we can show this. Remind me to do it after I finish this problem, after we finish this problem. So for now, we have the weight acting at the center of mass. Any other forces acting on the bar? Normals at where and where? A and B. So I have to be careful at B, because the seat is kind of inclined. 7 degrees was the horizontal. So maybe I'll draw it as a dashed line. So I'm going to have a normal force that's slightly inclined. And I also, do I just have a normal force at B? No, what else do I have? A friction force, right? Because if I didn't have a friction force, what would happen? Yeah, the bar would just slide. So I have a friction force at B. Okay, same thing at A. At A, I have NA and a friction force at A. Okay. Now, because the rod is about to tip forward, what happens to these forces? What is equal to 0? Exactly. The rod is losing contact at A, or is about, well, the normal force at A is 0. And if you were to decelerate a little bit more, the rod would tip over, right? So the rod is barely in contact at A, so that's why NA and FFA are 0. The normal force at A and the friction force at A are 0. Okay, the rod is about to tip forward. So then the only non-zero forces that are still acting on the rod are the weight. I can take a basis like this. Now I'm thinking, should I take a basis that is along the rod or that is vertical and horizontal? Oh, actually, I need to be specific that these two are not acting along the rod. So let me double check. Fix that. Yeah. That's perpendicular to this surface, that's NB. And the friction force at B. Okay, so maybe I'll take, I'll keep this. If I need another basis, I'll add it later. So the weight is minus mgey. The normal force at B is some unknown quantity which we need to determine, but we know its direction. Cosine 7 EY minus sine 7 gives you this. And A, sorry, FB. Cosine is that right? Do I have a mistake? Okay, so there are several ways to solve this problem. What I want you to do is to take a minute, think about how would you proceed to solve for the deceleration A for which the rod will begin to tip forward. So take a minute, think about how you would solve it, and chat with your neighbor about it, keeping in mind that there are different ways to solve this problem, right? Because we have different forms of the balance laws. The balance of angular momentum. I could choose form A. Could I choose form B here? Could I choose form B? Is there any fixed point on the rod? No, right? The rod is just translating altogether. So there are no fixed points. So I cannot choose B, but I can choose A or C, and I can have the liberty of choosing which material point I apply the balance of angular momentum about. So a lot to choose. Take a minute, think about it. How would you solve this problem? It's fixed on the car, but the car itself is decelerating. Yes. What do you think you're gonna do?
Since we want probably try and can we use the balance of linear momentum here?
Yes, yes, you can apply both equations. So go ahead, start with one of them. So yeah, if you don't know where to start, just put, for example, the balance of linear momentum, see what it's missing. What are you gonna do? What are the plans?
Well, I thought B would be like staying still. But
B? Yeah, but the car is moving, right? So it's fixed relative to the moving car.
Can we assume that the acceleration is only EX, or in the final answers from
What acceleration?
the the acceleration of the car?
The acceleration of the car is horizontal.
Huh?
Yeah, it is horizontal, the acceleration of the car.
Yeah, would that be in the? Would that be
Yes, you can
horizontal?
take Ax to be along the horizontal. You see they drew it here, yeah, yeah.
Thank you.
You're welcome. Sorry? So you apply F equals ma, and what are the unknowns? I'm guessing A, friction, so 3 scalar unknowns, but this is a vector equation in the plane. So you need the balance of angular momentum. But then which one? About the center of mass, about some other point? Did you, everyone please take a minute, write F equals ma, the balance of linear momentum for the rod. What is the acceleration of the center of mass of the rod, by the way? What is the acceleration of the center of mass of this bar? What is it? Yeah, it's the same as the acceleration of the car. Why? I mean, the rod, the car, the rigid body is moving. They're different rigid bodies. How come these two objects, they have the same acceleration? Yeah, but also because the body is just translating, right? So when an object is translating, all the points on the object, they have the same velocity and same acceleration. So the acceleration of any point on the bar is the same as the acceleration of the center of mass, which is the same as the acceleration of the car, just in the case where the bar is translating. Okay, and if you write the balance of linear momentum, how many unknowns will you have in that equation? Sorry. 3, right? A is unknown, and what are the other two? And B and FB. So 3 scalar unknowns, but F equals ma in the plane is 2 scalar equations, not enough. We need one more equation. We're going to use the balance of angular momentum. Now, which one? We can do it above the center of mass, definitely. But there's a more elegant way to do it. B, why?
Because the moment for 2 of the 3 forces is 0.
Right, if this, I sum up the moments about B, what is the moment of the normal force at B about B? 0. What is the normal force of the friction at B about B? 0. So I hide the moment of 2 unknown forces. So that's nice. Then which unknown would I be solving for when I sum the moments at B? The weight is known. What is the unknown that I will be solving for when I sum the moments about B? The length? I think, is the length of the rod given? I don't know. We will see. Let us see. Okay. So sum of moments about B. B is a moving point, right? So sum of moments about B, I'm going to use this form. Sum of moments about B is H dot C plus RC minus RB plus MAC. So now what is the acceleration? What is the unknown now we're solving for? AC. It's going to be AC. Because what is H dot C here? The angular momentum about the center of mass? 0. Why? Right, because omega is 0 and HC is IC omega. So when omega is 0, HC is 0 and H dot C is 0. So this term is 0. Okay, how do I calculate the sum of moments about B? That's just the moment of the weight. How do I calculate the moment of the weight about point B? Use a cross product. RC minus RB crossed with the weight, which is L over 2 cosine 30 EY minus sine 30 EX crossed with minus mg EY okay, is equal to RC minus RB, which is the same vector, crossed with M AC, which is, what is AC again? The acceleration of the center of mass of the minus AEX. So now I can take a cross product. That's going to be minus minus L over 2. The length is going to cancel out, so L over 2 and L over 2, bye-bye to you. So minus sine 30 degrees mg is equal to A cosine 30 degrees easy. Dot with EZ, I'll get that A doesn't even depend on M is G sine 30 over cosine 30. Cool. Any questions? Okay. So now what I want you to do is try to get any questions? Questions. I want you to try to get the same answer by using the balance of angular momentum about the center of mass, about C. So try to get the same answer, right? Because whatever method we use, the answer should be the same. To get this answer by using the balance of angular momentum about the center of mass. MC is equal to H dot C. Go ahead. That's a good question. How do we know that H dot C is 0 in this problem? Can anyone help? Why is H dot C 0?
Because I guess the current instantaneous angular velocity
It's not current instantaneous. It's not rotating. So omega is 0.
Yeah, but I guess the question says it's starting to
No,
tick
it
forward.
would rotate if the deceleration would to like magnitude would increase.
Okay.
But at this deceleration, it's not.
Okay, so it's the very upper limit.
Yeah.
Okay.
But it's not if you increase time at the second instant, it will rotate. No. If you increase the conditions a little bit, then it will rotate.
Okay. Makes sense.
And when you're done, let me know. And if you have any questions, also let me know. It's not going to be as simple as this, because you'll be solving 3 coupled equations for the 3 unknowns. They might be uncoupled, but 3 equations, 3 unknowns. Are you doing it? Are you working on it?
Just thinking, wouldn't the angle be like 27 degrees or something? Or sorry, like 23 degrees, because we have the 30 and then we have the 7 here. So we have
Well, 30 is with the vertical, right?
Yeah.
And I want the angle with the vertical because I took EX and EY to be along the vertical, like horizontal and vertical.
Okay, so then, gotcha. I was just thinking that like when we take the cross product, it's gonna be kind of weird because we have. Oh wait, no, it's.
Well, just put the formula and then plug in the terms one after the other.
That sounds good.
How is it going?
Confused on where to start.
So first, write the equation. MC is equal to H dot C. Okay, H dot C is equal to 0, right?
Yeah.
Okay, so MC is equal to 0. So now we have to calculate 0 vector.
Oh, sure.
Great. Now we have to calculate MC. How do I calculate the sum of moments about the center of mass? How many forces are acting on the rigid body?
It's just like the
3, right?
Yeah.
Okay, so the weight is at the center of mass. So what is the moment of the weight about the center of mass?
0.
0, perfect. 1 is gone. The other two. The other two are applied at point B.
Yeah.
What are their moments above the center of mass?
The force is times by the distance between.
You have to use the cross product definition for the moment, okay? So RB minus RC cross
Yeah.
the two forces,
Yeah.
sum of the two. How is it going? Okay, so the equation is H, as you see it, HC is equal, MC is equal to H dot C, like dot is above. Yes, and the C is above. So it says about C. Okay, and H dot C is a vector, which is equal to 0. Why?
Is the moment about C is 0?
Why? Because what is the angular velocity omega for the rigid body?
0?
Why?
It's
It's
not moving.
not rotating, right? So did you see the equation up there on the board? HC is equal to IC omega, the upper board third equation. HC is IC omega. When omega is 0, then IC omega is 0, then HC is 0.
I see.
Yeah. So then the sum of moments about C is 0. How do you calculate the sum of moments?
With the equation.
The sum of moments, you should be able to do this from statics. It's the vector from where you're calculating the moment about to the point. So RB minus RC. So here I'm calculating the sum of moments of NB and FB.
Oh, just like the distance times the force.
Yes, but we're using vectors. So everyone, we need to know this. The moment of a force, that's things we know from statics. And if we don't know this, we cannot pass dynamics. Okay, the moment of F so the sum of moments about A here is gonna be RB minus RA crossed with F. So always when I'm trying to calculate the moment of a force about a point, it's the vector from the point to the force crossed with the force. RB minus RA cross F. We need to know this. We should have known this from high school, if not statics. So you're done?
No, I'm still trying to process. So basically, you're saying that NB is equal to, in this case, MA, because weight force is the only one that's causing a moment, right? Because the normal force is pointing, or NB is pointing at B. The friction force of that B is also pointing at B, so it equals to 0, so you're only left with the weight.
Okay, so this is how I calculate the moment of this force about point A, right? But if A and B are equal, are the same, how to calculate the moment of this force about this point? I'm gonna be left with RB minus RA, but if they're the same, then it's the moment is 0. Yes. So always when you're calculating the moment of a force that passes through the point you're trying to calculate the moment about, moment of the force is going to be 0. It's kind of like I applied a force that's giving a moment about this hinge. But if I apply a force at the hinge, it's not going to move the door. The moment of the force about the hinge is going to be 0. How is it going? Are we finished?
Close. So we have the two moments acting about it. It's going to be MB and F.
Yeah, the moment of the normal force and the friction force at B, exactly.
Because weight is cancelled out, well, 0.
Yes.
C.
Yeah.
So we're missing one more now.
What is it? I don't think you are.
No.
Right, sum of moments about C is H dot C, which is 0. Sum of moments about C is the two forces, the moments of the two forces at B. That's their moment sum should be equal, about B should be equal to 0.
Inner balance of the momentum is,
Yeah.
equations are still the same. Okay.
Yeah. Where's your solution?
For which problem are we doing?
Problem 1.
Oh, shit.
So, how we doing? You haven't started yet?
No.
When?
Oh, just in a second.
Yeah.
I'm getting a really weird solve path here. Start taking the cross product of the
Yes.
RB and then I get this big old thing.
You can do this.
So does it, I guess, does this allow us to do anything further? I guess
What is it?
I get that,
There's something wrong because you should get a. Okay, that's the equation you get. It's along EZ. Okay, so that's one equation, right? And then you need two more.
momentum.
Yeah, balance of linear momentum. You get two more, then three equations to your nodes.
Gotcha.
So you're good.
Thank you.
I just want you to solve it so that I can help you out. So if you have any questions, just let me know. It's not meant to be intimidating.
So we're trying to find FB.
We're trying to find, well, what I want you to do is I want you to apply the balance of angular momentum. MC is equal to h dot c about the center of mass. I want you to apply this equation A about the center of mass.
Just clarify, for the reason why the moment in the center of mass is zero, it's like the angular momentum of the center of mass is zero is because even if you went like the center of mass is essentially like.
Not quite. Why is, so you're asking why h dot c is 0?
Yeah.
Why is h dot c 0?
So
Why is h dot c 0? What is it?
The system is only translating to the variable.
Exactly. The bar is just translating. So what is the angular velocity? 0. So omega is 0. So hc is ic omega. So since omega is 0, so you see the third equation on the top board? Because omega is 0, hc is 0. So its derivative is going to be 0.
But if it was rotating, then omega would no longer be.
Exactly. Which we're going to talk about the case in a bit. Okay, but in this set for all the problems you're talking about, the bodies are not rotating, so omega is going to be 0. Done?
No, it's just not right. I don't know.
Okay, but you got your equations, 3 equations.
I think so.
Can I look at the balance of angular momentum?
Use my profit and I go F and B in terms of FB,
Okay.
but it might not be right.
How did you do the squash product? RB minus RC. Yeah, how did you do it?
So this is
RB minus RC is L over 2.
EY and the X term, and then I just
I think you have a sign mistake, right? Because RB minus RC should point along negative EY, positive EX.
Zero is equal to the moment.
yeah.
And B is
Yeah.
So we just take that derivative.
Okay, then the cross product. So L over 2, for example, cosine 30 EY times minus sine 7 EX. It's gonna be minus, and then you're gonna have it on minus cosine. Yeah, yeah, yeah. Maybe it helps.
MC is equal to 0, and then you have, that means that the moment that the friction force causes and the normal force causes the moment.
How's it going?
Yeah, but then you have, you're just left with, yeah, the creature.
I'm like one equation away, but I need
Did
to
you calculate the
plug
cross
everything in.
product? Okay, great. You got one scalar equation. So if you project this along EZ, that's one scalar equation for the two unknowns, friction and normal force. Okay, so you have one equation, two unknowns. You need more equations, which is going to be the balance of linear momentum, F equals MAC. That's 2 more equations, 1 more unknown, so you have 3 equations, 3 unknowns that you can solve for.
Okay, thank you.
Did you write the balance of angular momentum about the center of mass? MC is equal to H dot C plus RC minus RP.
And then the distance from here, from the center of mass to here, and then just L2.
Okay, so you did get the answer quickly, right?
And then I'm solving it right now.
Okay. Okay. Yeah, what I meant for you to do is to, okay. So this term is going to be 0 also because you're going to do RC minus RC because your P is C here. So you're going to left with MC is equal to 0.
Oh.
Yeah. Because RC minus RC, you took P to be C, right? How do you calculate the sum of moments about C?
The sum of moment would be like B, the force of B, and then the distance to here.
Yes, but calculate the moments using vectors. Your friend there knows how to calculate. What's your name? Are you okay at calculating moments of vectors now? Moments like vector equations? Yes. Yeah. So, yeah. If I want to calculate the moment of this, the forces here about this point, it's the vector from here to here.
For which is L2. Negative sign EX, then cosine of the
Yeah.
and then plus the MB and then
Yeah.
component.
Good. Okay. Any questions?
So the moment is 0. So you
No,
said
the moment is not. The sum of moments of the normal and the friction should sum to 0 from the balance of angular
from here,
momentum.
MC
Yeah.
is gonna be 0 because
Yeah.
RC minus RC equals
Yeah.
0. So
Yes.
Okay. I see.
Great.
Can you just check?
Of course. RB minus RC. So you're done behind me, you two? You two are done? Yeah? You got the answer?
No, not me.
How did you stop working if you're not done
I
yet?
just wrote out how to find it because I didn't want to do all the algebra.
Wait. And then the first time you do it will be an exam? That's your plan?
No.
So,
I just don't want to
come
do
on.
any. I just don't want to do algebra right now.
Are you done?
I have it down to what I would substitute into the.
Okay, so you have the scalar equations. At least obtain the scalar equations. That's not algebra, that's dynamics, what you're supposed to do in a dynamics class. Okay, well, you got the scalar equations. Can I just, sorry, take a look?
I start.
Yeah, okay. Okay. And you do the cross product using these? Okay. Okay, cool. So raise your hand if you have the 3 scalar equations you're gonna use. Yeah, 1, 2, you have the 3 scalar equations. Okay, 2 more minutes for everyone to get the 3 scalar equations. If you don't have them, you have questions, ask me or ask the neighbors around you. At least get the 3 scalar equations you're gonna use to solve, and then you can plug them into the computer and solve them. What is it?
So that's why the way you consider
just the forces out of the
scalar forces, and then you're able to relate NB to FB, and then you put it back into the
Hey, I just want to check your equations real quick.
Oh, I messed up a little, so then I had to restart. But
Okay.
to do this, like 0 equals
Yeah.
R and then both of the forces.
Yes. Okay. Then you need to put in big parentheses, but yeah.
Yeah.
Cool.
The gyroscopic term would be 0, right?
What's gyroscopic term?
The,
Where did you get this equation from?
I just looked up balance of
It's on the board. MC is equal to h dot c.
yeah,
Yeah. Yeah. What is omega here?
angular velocity.
Which is what for the bar?
Wouldn't it be between
For the bar, the rigid body, which is AB. Sorry.
at the moment of
Throughout the motion.
well at
Is the bar rotating?
it's
Throughout.
about to rotate.
It's about to rotate if you were to change the conditions, the parameters of the motion a little bit. So it's not that at the next instant it will rotate, it's that if you change the acceleration a little bit, it will rotate.
So well right now it's 0.
Yeah. Yeah. And then later at the next instant it's going to be 0. It's only going to rotate if you change the deceleration of the car. So what is the angular velocity of the bar?
0. And so is the angular acceleration.
Yeah. So what are these terms that you have there?
0.
You're not allowed to use any equations that you cannot show where they come from.
Okay.
Okay? Go. Any questions, anyone, before we move on? Questions, questions, questions? Yes.
So once we get to here with all like the angular components, we're just like defining one of them and then substituting them back into one of these.
Yeah, so you have 3 equations, 3 unknowns. You're going to have to solve somehow. This you can project along easy and get like 1 scalar equations, 2 scalar equations, 3 equations, 3 unknowns you can solve.
Okay.
It's a linear system, so you can technically put it into a matrix and solve it in like MATLAB or, yeah. Okay, we're moving on. Any objections to us moving on? Okay. 3, 2, 1, no objections, great, okay. So now what I want to do is I want to calculate the derivative of the angular momentum for problems where omega is not 0. So how do I calculate the derivative of h dot c if omega is not 0? And yes, you are right. The problems are going to be long from now on. So you have to spend a bunch of time practicing these problems. So that it's going to take time. It's normal, okay? And if you have questions, you let us know. Okay. Okay. I'm going to try to do this in a couple different ways. So I'm going to first start with HC is equal to IC omega, right? Okay, if I write this in matrix form, this says that, or not even in matrix form. Let's not do matrix form. So that's the tensor IC IJ EI bond EJ. Apply to the vector So this is a shorthand for omega 1 or omega 1 E1 plus omega 2 E2 plus omega 3 E3. So omega x EX plus omega y EY plus omega z EZ. So these developments are general for like the angular velocity being any vector in 3D. Okay. And this is another notation for the tensor. I11 E11 E1 plus I12 E2 E11 E2 plus and so on, 9 terms. Okay. So I can take all of the sums to one side, I, j, k, and now each tensor is applying to each vector here. So what was the definition of the bond product? Remember, A bond B applied to C is equal to B dot C applied to A, right? So I'm taking all the scalars to the side. Okay. EI bond EJ applied to EK, that's going to be EJ bond EK, sorry, EJ dot EK along EI. Okay, take a minute. Is your neighbor okay with this? Any questions so far? So I'll do it using matrices again, so that just another way using matrices should be a little bit easier, but just wanted to show you this. So any questions about this? Questions? Okay. So remember, J and K, they go from 1 to 3. So basically, J is E1 if J is equal to 1, E2 if J is equal to 2. So that's E1, E2, E3. EK is also E1, E2, E3. So what can you say about this dot product? It's like taking the dot product of EX dot EX or EX dot EY or EY dot EZ. What are the two possible values of this dot product? 1 and 0. In which case is the dot product 1? Exactly. In which case is the dot product 0? If they're different, right? So EJ dot EK is equal to 0 if J different than K, and it's 1 if J is equal to K. Does that make sense? So basically, all the terms when these two are different are going to be 0. So I'm just going to keep the terms when they are equal. So I'm going to say that J and K are equal. So that will be the sum of I, J, I, C, I, J, omega J, E, I. So what did I do? I said that when J or K are different, this term is 0. So it cancels out the term from the sum. So I just kept the terms in the sum where J and K are equal. So I replaced K by J. So now it's a sum over two indices. Okay. So now I have this, that HC is IC omega is equal to the sum Ij of ICIJ. So basically, if I remove the sum, that's just IC11 omega 1 E1. I'll do a simplification. Okay. So IC11 omega 1. No, I have a omega JEI. Yep. IC11 omega 1. plus IC1 2 omega 2 plus IC1 3 omega 3 E1, okay, plus IC2 1 omega 1 plus IC2 2 omega 2 plus IC 2 3 omega 3 E2 plus IC So this is basically just the same equation, but I didn't use the sum anymore, just for you to see. So I want to calculate H dot C. Any questions before I do that? Questions? I want to calculate H dot C. Okay, my question is, what in this HC equation, what are the terms that depend on time and what are the terms that are constant? Exactly, the inertias are constant, right? They're expressed on the correlational basis, the mass distribution relative to the correlational basis are constant. What is changing in time? Omega 1, omega 2, omega 3, and the correlational basis, right? So when I take the derivative of this term, this is changing in time and this is changing in time. So H dot C, now it's the sum of over ij, ic, ij, omega dot j, ei, so I'm using the product rule, plus omega j ei dot. It's just much easier not to write all of this, but to use the indices in this notation. I'll split the sum into two. Can anyone remind us what was ei dot? How do I take the derivative of a correlational basis vector? Exactly, omega cross ei. So I'm going to replace this by omega cross that. Omega cross ei. Right, because ei dot is omega cross ei. So now I have two terms. This first term, I'm going to call it HC corrotational, and the second term is omega cross HC. Right? Omega cross HC, that's the same term. Remember, we used this corrotational symbol before, right? We used it before. Where did we use it? Exactly. So, and what did it mean? What did the correlational derivative mean? It's the derivative assuming that the basis is fixed. Okay? So here, it's the derivative of the angular momentum assuming that Ej is fixed. So that's the term that's changing due to the change in omega, assuming that the basis vector is fixed. And the other term is due to the change in the basis vectors. Okay? So this is H dot C. This is a general term that this is a general equation that applies in 3D. Okay? Now, for the purposes of this class, we're considering mostly problems of planar rigid bodies we're going to take the angular velocity to be along EZ. Okay, so if the angular velocity is just along E3, so it's just omega 3, then all the omega 1 terms and omega 2 terms are 0. So these equations simplify. HC just has these 3 terms left now. I see. Okay, and H dot C becomes IC13 omega dot 3 minus IC23 omega 3 squared E1, right? Because E dot 2 is going to be omega plus E2, which is 3, 2 minus, yeah, plus IC 2, 3 plus IC 1, 3. This is omega dot 3 omega 3 squared E2 IC 3, 3 omega dot 3 A3. So this is the equation we're going to use in this class when omega is just along E3. And in some problems, it might simplify even further. In some problems where the products of inertia are 0, it might simplify even further. So if the products of inertia are 0, then these terms go away, these terms go away, these terms go away, these terms go away, you're only left with this term if the products of inertia are 0. One more thing I want to say is that the angular acceleration alpha is the derivative of the angular velocity. Alpha is omega dot E3. Okay, take a minute, think, let me know if you have questions. There should be questions, so I'm waiting for questions. Yes, there is a step I missed, so you can double check it and make sure I have it right. Can you take one and pass, please? Thanks. Okay, please ask me questions. Questions. Do you have questions? great question. So I'm taking the derivative of this, right? So this depends on time, this depends on time, this depends on time, this depends on time. This one is fixed, actually. So when I take the derivative of this term, I get two terms using the product rule. One of them is this one, I13 omega dot 3 E1. The second one is going to be I13 omega 3 E1 dot. E1 dot, which is going to be omega cross E1, which is going to be this term. So I did skip a step there. The step I skipped is taking the derivative using the product rule and replacing EI dot by omega cross EI, where omega is this. So if you do the calculations, you should get the same answer. Yes?
So why does that go to E2?
Okay, good, because you're doing E1 dot is equal to omega cross E1, which is omega 3 E3 cross E1. And what is E3 cross E1? Minus E2. Yes. Does that answer your question?
That's
Positive? Sorry, plus. Yes, that's why I have a positive here. Yes, you're right. Okay, what about E2 dot? E2 dot is what? Take a minute, do it. And what is E2 dot? Do the calculation. Yeah. Now E3 dot is 0 because E3 is constant, okay? So if you look at set 20, any other questions? There should be more questions, yes.
What does the product of inertia times like omega mean physically?
What I can say is that it has to do with the mass imbalance creating a moment. For example, if you have a washing machine, it's rotating, right? If the clothes are evenly distributed on the rim of the washing machine, it will rotate about the axis of rotation. The center of mass of the clothes, it is at the axis of rotation, it's going to rotate, no problem, right? If I have a washing machine, I'm putting a bulky item in there, the mass is not evenly distributed. So the center of mass is off center from the center axis of rotation. The products of inertia are non-zero. What is going to happen to the washing machine? Is it going to rotate smoothly? No, it's going to shake and jump because this uneven mass distribution, these non-zero products of inertia are creating moments, not just about EZ, the axis of rotation, but about the other axes, E1 and E2. So you see they're creating moments about E1 and E2 and not just E3. So that's where they come in physically. Another example of this is that if you're driving a car and the axis of the wheels is off center, so what do? They add small masses to the wheels to center the center of the wheel is the axis of the car, or else you're not going to have a smooth ride. Okay? Yes?
How does the justification work that we're taking it when j is equal to k?
Oh, here?
Yeah.
Because otherwise, in all other terms, when j or k are different, the term is going to be 0. So you're going to be summing a bunch of 0 terms, so I got rid of them. And I just left the terms when j is equal to k. And that's a great question. Another way to see it is to actually remove the indicial notation and do it number by number, step by step, and you will be able to see it. It's just going to be long. Not difficult algebra, just long. Yes, there was a question? Okay. Okay, so I just wanted to have you look at the set 20. So you can see equations 5, 6, and 7. Okay, so equation 6 is the one I have on the board. Equation 6 is the one we have on the board, right? Equation 5 is the same as 6. Why? But that one is about O. Here, if I look here, if I consider a fixed point O, what is HO? Oops. if O is a fixed point, I get that VO is 0, right? So HO is going to be just IO omega. So the derivative of this and the derivative of that, they have the same form except that instead of C, I put O. That's why 5 and 6 looks very similar. Now 7 is a little bit different because it contains the derivative of IP omega, which is the same as what we did, plus it says d by dt, the derivative of this term. Okay? So that's 7. Same steps to do the derivative of IP omega, except to replace P by C, C by P, sorry, and then the derivative of this term. So you should not forget the derivative of that term. Usually I will never use HP. Usually I will use this form of the balance of angular momentum. MP is equal to H dot C plus this terms. Usually that's what I do, so that I don't have to take the derivative of these extra terms at the end of IP. Okay? That's all for today. Thank you all for coming. And I do have office hours from 12:30 to 1:30 today.